Hi everyone. In this lecture, we'll discuss about the Q of the series RLC circuit. So there are several definitions of Q that we have been using so far when we spoke about parallel RLC circuits or lossy capacitors and inductors. So here there are several definitions of Q which I've written here. So we'll go one by one and try to find Q for a series RLC circuit. The first definition of Q is nothing but since it's a series RLC circuit, I already said the one with the larger impedance matters. Now Q tells you how reactive the circuit is. Okay, Q is a metric that tells you how reactive the circuit is or how energy storing the circuit is. So it makes sense to take the definition, the ratio of the reactive impedance by the lossy impedance, XL upon RS, the lossy part of the impedance to the reactive part of the impedance. So using that, we can write Q as omega naught L by RS. Now here we should understand the reactances of inductor and capacitor. Okay, the impedances of the inductors and capacitors, they actually vary with frequency. So therefore Q is also a function of frequency. But normally we define Q at omega naught, where omega naught is the resonant frequency 1 by root LC. Okay, because this once we define Q in this way, this Q actually features when you characterize the frequency response of resonant systems. Q figures in many properties of such a resonant system. So that's why Q is especially when you define Q at the resonant frequency. Okay, so we can also define a few properties of a resonant system. For example, when I say a resonant system, it's mostly a system with a behavior which is actually a frequency selective behavior like this. If you plot the frequency response of a resonant system, it actually is going to have a behavior like this. Now Q tells you, it can tell you how selective or how narrow this shape of the function can be. So we'll discuss about this in the coming lectures. So that's why Q is a very important metric. It can actually tell you certain information about the frequency response of resonant systems. So in this lecture, we'll see how to define Q for a series RLC circuit. Now Q here is omega naught L by RS by the first definition, or this is also equal to 1 by omega naught RS into C. Okay, and we know that at resonant frequency omega naught L will simply be equal to omega naught C. Now the other definition of Q is to use the average power lost or stored in the inductor, peak to peak of it, divided by the average power which is lost across the resistor. Again, since it's a series RLC circuit, we can very easily see that if I'm trying to compute this, its power is generally I square times R, I square times the impedance. Okay, so in this it's going to be I square, I is same for both, and times I square by RS. So this reduces to the first definition itself. We'll actually get omega naught L by RS. By just looking at the expression, we can write it. Okay, I square XL by I square RS. But I'll try to derive the expression for power which is dissipated in the inductor and capacitor, so it gives you a better intuition actually as to what exactly happens at the resonant frequency. So what we are going to do is we are actually going to drive a series RLC circuit by a sinusoid whose frequency is equal to the resonant frequency, and then see what happens, what is the power dissipated across each element in this circuit. Now we know that at the resonant frequency the impedance of the inductor is j omega naught L, okay, and impedance of capacitance is minus j by omega naught C, which is also equal to omega naught L. I'll simply write it as this is actually minus j by omega naught C. So in fact the impedances are same but with negative signs. It's purely imaginary. Of course inductive impedance is pure and capacitive impedances are purely imaginary, but they are perfectly out of phase it's out of phase at all frequencies. Okay, at the resonant frequency the magnitudes are also same. So we said at the resonant frequency both the inductor and capacitor will behave like a short circuit. It's just going to behave like a short circuit, and you'll only have the voltage source will only see the resistor. So the current flowing in this circuit will simply be Vp by R Rs into cos omega naught t. Now if I try to find the power dissipated across the resistor, so PR, it's simply going to be V of t into I of t. This is the instantaneous power. So which is going to be Vp square by Rs into cos square omega naught t. Now if you look at this power across the resistor, it's always positive. Okay, I'm sorry. So it's actually always positive. So it's always positive, indicating that resistor can only absorb power. We have already discussed, if the power is greater than 0, then the element absorbs power. If it is less than 0, then it delivers power. Then we will try to find what is the power delivered by the voltage source. I will call it PV of t. That is simply the same power dissipated across the resistor with a minus sign. Okay, so which means the voltage source is always delivering power to the circuit. It is always delivering power to the circuit. Now we have already discussed that if I have an inductor or a capacitor, when you apply a voltage or current across it, in one cycle it will deliver and the other cycle it will absorb power. It could both deliver and absorb power when you connect it to a reactive element. So then here it tells you that when PV is minus of this, power is always negative. The power delivered is always, power absorbed by the voltage source is always negative, which means it is delivering power. Okay, so what happens to the power across the inductor and capacitor? In a similar way, we will compute, we know the current I of t, it is Vp by R cos omega naught t, Rs cos omega naught t. So to find the voltage across the inductor, I will simply use L di by dt. So you will get L into Vp by Rs into omega naught sin omega naught t with a minus sign. Okay, so this will be the voltage VL of t. Similarly, you can find the capacitor voltage. We can simply use this basic result. Capacitor voltage will be negative of the voltage across the inductor, because we just saw that from these equations. The impedance is purely negative. Impedances are actually 180 degrees apart. I mean, they both are out of phase. Okay. So therefore, since current is same across both, so the voltage signs will be different for the inductor and capacitor. If inductor voltage is negative, then capacitor voltage will be positive. I can simply write it as omega naught L into Vp by Rs sin omega naught t. Okay, so this voltage I derived it by L di by dt, and this voltage I simply use the fact that the voltage across the inductor, because we discussed that at the resonant frequency, the voltage across the inductor, if you recall from the last lecture, we said these two voltages were of opposite polarity, such that the inductor and capacitor behave like a short circuit. So therefore from that Vc, so we got an equation that Vc of t plus Vl of t is equal to 0. We got this equation because both the inductor and capacitor impedances are exactly opposites of, negative, both the impedances have different polarities. So therefore since current is same, the sum of the two voltages is 0. Now the current flowing through that circuit is simply given by Vp by Rs into cos omega naught t. So I'll have to just take the product of the voltage into current to find the power dissipated in the power absorbed by the inductor. So here when I simply multiply this, I'm going to get Vp square by Rs square into omega naught L into half of sin 2 omega naught t. Okay, I can just cos into sine. When I multiply cos omega naught into sin omega naught, I can express it as half sin 2 omega naught t. And the power dissipated through the capacitor is actually minus Vp square by Rs into omega naught L into half of sin omega naught t. sine 2 omega naught t. Sorry. So here actually the power inductor is negative and capacitor is positive. There is a negative sign for the inductive voltage. Now if you look at this result, if you try to plot this equation, here power can be both negative and positive. So for the inductor, it's actually a function, the frequency of the instantaneous power is 2 omega naught, twice the applied signal's frequency. Okay, and the capacitive power on the other hand, it's simply the negative of the inductive power. So here we can see that in this cycle, in the positive cycle, if capacitor is absorbing power, inductor is delivering power. Okay, and when inductor is absorbing power, here capacitor is delivering power. Whenever power is negative, it's delivering. So therefore these two, inductor and capacitor, the power is going back and forth between inductor and capacitor. So you have an inductor, capacitor, L and C. As far as the voltage source is concerned, the voltage source power doesn't have to deliver any power or absorb any power from these elements, because the sum of the two powers, if I try to find PL plus PC, is simply equal to 0. The power dissipated across the capacitor plus inductor is always is equal to 0. So as far as the voltage source is concerned, they just behave like a short circuit, as though it's not taking any current. Okay, and I mean these two circuits, I mean without an inductor, if I just replace this by a short circuit at the resonant frequency, so these two circuits are equivalent. Okay, also you can see this result directly follows from the direct equation that Vc of t, the voltage across the capacitor and inductor, the sum of the two is equal to 0. So I just have to multiply by current on both the sides, I of t on both the sides. I'll be directly getting this result. Pc of t, the instantaneous power across the capacitor and inductor, is actually equal to 0. Okay. So from this we obtained a result for the power dissipation across the inductor and capacitor, and we also found the power dissipated across the resistor, which was given by this. Okay, there is Rs square here. Sorry. So I'll write the power dissipated across the resistor, which is Vp square by Rs into cos square omega naught t, and the power dissipated across the inductor or the capacitor, I mean of course I'll take the magnitude alone, I'll take the magnitude of it, okay, is Vp square by Rs square into omega naught L into half sine 2 omega naught t. So if I take the peak to peak ratio, the peak to peak value of this and the peak to peak value of this, I'm going to get this term by this term. So you will simply get, I mean the peak to peak value of this is 1, half sine 2 omega naught t into 2, you will get 1, and this, it goes from 0 to 1. Okay, so the peak to peak value is 1 again. We have already derived this for parallel and lossy inductors, so you can go through that. So then you get omega naught L by Rs. This is also equal to 1 by Rs omega naught C. So this is the other definition of Q. So for a series RLC circuit, Q here is omega naught RL by S, omega naught L by Rs, or 1 by omega naught C Rs. Just to quickly refresh your memory, for a parallel RLC circuit, your Q is Rp by omega naught L. Okay, so there again, if you can use the same definition, we derived it. It was Rp upon omega naught L, or this was also equal to Rp into omega naught C. This is for series RLC circuit. Okay, now the third and the final result is 2 pi into energy stored across the, sum of the energy stored, the peak energy stored in the circuit, divided by energy lost, which was simply equal to P average into T, energy lost per cycle. This was energy lost per cycle. So to find that, we can find what is the energy stored. So that is simply half C, and this is the instantaneous energy stored across the capacitor, half C voltage square. So the voltage across the capacitor, again, how do we find it? We just derive the time domain expressions for current. At the resonant frequency, the current was Vp by Rs into cos omega naught t. And we said if you know the current, we can compute the voltage across the inductor, which was the derivative of this, which was minus Vp by Rs into omega naught into L. It's L di by dt. So this is the current. If you do L di by dt, you get the voltage across the inductor. So with the minus of this Vc of t is simply minus of VL of t. So from that we get the voltage, which is same as this. So when I square it, I'm going to get Vp omega naught L upon Rs the whole square into sine square omega naught t. Okay. Now similarly, we can try to find what is the energy stored across the inductor. That's going to be half Li square. So I is again half L Vp by Rs the whole square into cos square omega naught t. Okay. Again, we can simply use this result that LC equals 1 by omega naught square, or omega naught square equals 1 by LC. So L will be simply omega naught square C. Okay. So this expression I can reduce it to half. L can be written as 1 by omega naught square C. Okay. So this result becomes Vp square by Rs square, okay, into, or we'll write it in terms of L. That must be easier. So this must be half L. So here, if you look at the energy across the capacitor, you can write it as half C, and I'll take omega naught L the whole square out. So you would get Vp by Rs square sine square omega naught t. Now this term here, omega naught, if I this term here, it's simply 1 by C. You can see omega naught square is 1 by LC. Okay, so we can easily show that. So C into omega naught square L square. So I'll write omega naught square L into L. So this is simply going to be L. So energy EC of t is simply half L Vp square by Rs square. I mean, omega naught square is 1 by LC, so these two terms will cancel out and you will get L. The expression for energy stored across the capacitor is, the value here is same. The only thing difference is it's sine square instead of cos square. For a capacitor it is, for inductor it is cos square. Now if you add the two values, the total energy stored, the total energy stored in both the capacitor and the inductor, you're simply going to get half L Vp square by Rs square. The sum of sine square plus cos square is 1. So you will simply get this as your total stored energy. Now we know that the average power dissipated, the total power dissipated across the resistor is simply Vp square by Rs into cos square omega naught t. Now this can also be written as Vp square by 2 Rs into 1 plus cos 2 omega naught t. Now the average value, if I compute the P average stored across the capacitor, across the resistor, energy dissipated across the resistor, it will simply be Vp square by 2 Rs. Okay. Now this, if I use the definition of Q for this, I'm going to get 2 pi into half L Vp square by Rs square, the whole divided by half Vp square by Rs into T. Okay. So this simply reduces to 2 pi by T is omega naught. So it reduces to omega naught L by Rs. Okay. So this is the average power dissipated into T. You'd get the same definition. You'd get the same value for Q using this definition as well. Okay, so with this we define the Q of a series RLC circuit. So for a series RLC circuit, to summarize, the Q is omega naught L by Rs, which is also equal to 1 by Rs omega naught C. Okay, in the next lecture we will try to analyze the frequency response of a series RLC circuit in more detail. Okay, using the definition of Q that we have used now, you will see where does the Q figure in when we discuss about the frequency response of a series RLC circuit.